It's my pleasure to have you in class once again today. The topic for today's class is work, energy, and power. You might ask yourself, why are we discussing the three topics together? They're actually different concepts, but they have to be taught together because you cannot seemingly detach them from one another. So it is difficult or seemingly impossible to discuss physics without having a recourse to this concept, that is the concept of work, energy, and power. So let us take a brief introduction into what each term is, starting with work. Work is actually the phenomenon that has application in our day-to-day activities. It has an application in our day-to-day activities, and it is said to be done when an object is acted upon by a force of which that force compels it to move in a particular point of application through a distance. So mathematically, we can say that work is equal to the product of force times the distance. Product of force and distance. So we have this to be F times S, or F times D. Some texts write it as F times D. They are still the same thing. Now, having said that, it is expedient to discuss what the unit for work is. The unit of work is equal to joule. That is, it is measured in joule. And we say that 1 joule is the work done by a force, is equal to the work done by a force of 1 Newton in moving a body from one particular point through a distance of 1 meter. 1 meter, and it acts in the direction of the particular force. So 1 joule equals 1 Newton, which moves a body through a distance of 1 meter. Now let us take a pictorial or diagrammatical representation of what we are trying to talk about. Let's say we have an object. This is the object lying on an horizontal plane. Let's call this the horizontal plane. And a particular force compels this body to be moved along this horizontal plane in this direction. Let's say this is the force F, and it moves it through this point to a particular point, to this particular point. Realize that work has been done on this body. Why? Because a force compels it to move through a particular distance. So let us call the distance S, that is, this distance to this place is distance S. So the work done by this particular body is simply the product of the force acting on the body and the distance. We said it is measured in joule. So we can also have, in some cases, where the object can either be pulled or can be pushed. Okay? So if the body is pushed, work is also done, or if the body is pulled, work is done. So if the force is inclined at a particular angle to the horizontal, then our work done will change from just being force times distance to the force times distance times the cosine of the angle in between them. So we have W equals Fs cos theta. Now, what if the angle is inclined perpendicular? This is the sign for perpendicular. So perpendicular to the motion. The force is inclined perpendicular. You know what perpendicular is now? It is inclined at an angle 90 degrees to the motion, of course, theta becomes 90 degrees. And if you check the cosine of theta, which is cos 90, of course, cos 90 is going to give us 0. Therefore, if you substitute the value into the formula for your work done over here, we have that W will be equal to Fs cos 90, which is equal to Fs times 0. Of course, anything multiplied by 0 is going to give us 0. So the work done when the force is applied perpendicular to the motion is equal to 0. This is a suitable exam question, OBJ, objective question. I might just ask you, what is the work done when a particular force is applied perpendicular to the motion? Of course, there is no need to solve that at all. Just go straight to your option and click the option that has 0 as the answer. It's as simple as that. Now, to further discuss what work done is, then I would like to take a particular example from the JAMB questions. From the JAMB question we have here, JAMB 2013 question 14. The question is, calculate the work done when a force F is equal to 20 Newton stretches a spring by 50 millimeters. So if the stretch is applied, if the string is stretched, then we have E to be equal to 50 millimeters. That is, the extension is equal to 50 millimeters. The question is by the implication is by how much is this string extended. Is that okay? Now, if we have this, remember we have to convert all our values to the standard unit. So if we convert 50 millimeters to meters, so we have 50 over 1000, which is equal to 0.05 meters. So having done that, we can substitute our values into the particular equation and get our answer. So we have work done in a string is equal to half of the force times the extension. Half of the force times extension, which is equal to 1 over 2 times 20 times 0.05. And if you do that, we have, this is 10, to give us 10 times 0.05, which is equal to 0.5 joules. So therefore, the work done by the force 20 Newton to stretch a string by 50 millimeters is equal to 0.5. And in that particular year, we have the options A to be equal to 0.5 joules, option B equals 1.5 joule, this is 1.5, option C equals 2.0 joule, then option D gave us 2.5 joule. Of course, we know that our answer is equal to 0.5 joule. This is just a simple application. Let us take one more example which seems a little bit more complex than the first one we had. The question is seen in JAMB 2010 question 8. The question is, a bulb of weight 0.1 Newton, the weight, that is the force acting on it, the force of the body or bulb in this case is 0.1 Newton. It hangs from a massless string of length 50 centimeters. So the length of the string is 50 centimeters. And we are told that a variable horizontal force which increases from 0 is applied to the bulb until the string makes an angle of 60 degrees to the horizontal. So our theta is 60 degrees. The question is, find the work done. The work done is what we are looking for. This is very, very easy, but can be illustrated using this particular diagram. So we're told that the bulb hangs on the mastless spring. Let us have this. So this is the string. This is the length. Let's have it this way. So this is 0.1 Newton. We're told that it hangs from a massless string. This is the string of length 50 centimeter and a variable horizontal force. Let us call this the variable horizontal force, which increases from 0. Let's call this point 0 until it increases from 0 is applied to pull the bulb until the string makes an angle of 60 degrees. So it's kept on pulling it until this particular bulb makes an angle of 60 degrees to the horizontal. We are asked to find the work done. So realize that this length is L, which is equal to this length over here. So we have this L to be equal to 0.5 meters. Of course, if you have 50 centimeters converted to meters, this will give us 0.5 meters. That is 50 over 100. Now, having said that, we can split this into two, where this point could be called Y and this other point could be called X. So if we have this, we can say that our length L is equal to Y plus X. And since L is already given to be equal to 0.5 meters from the question. Now, to move a step further, we can make X the subject of the formula. If we say X is equal to 0.5, then minus Y. The question I'm sure you might want to ask is, what is X? What is X standing for? So we would say, let us recall that X is the distance moved in the direction from the question. X is the distance moved in the direction of the force when the body is released. So when the body is released, the distance moved in the direction of the force is equal to X, and it can be represented in this section over here, from here to here. So having said that, we can decide to find the cosine of the angle. Let's look for the cosine of the angle theta. And if we do that, we have that cos theta, which is equal to cos 60 degrees, is equal to adjacent all over our hypotenuse from trigonometric functions or ratios. So cos theta equals adjacent. From this particular diagram, what is our adjacent? Of course, our adjacent is represented by y. So cos theta equals y, cos 60 equals y all over. Our hypotenuse is equal to 0.5. And if we do that, we will have our y to be equal to cos 60 degrees times 0.5. If you punch your calculator or use your trigonometric identities, you realize that cos 60 degrees is equal to 0.5, which is same as 1 over 2 times 0.5. If you multiply through or divide through, you realize that y is equal to 0.25. Y equals 0.25. Why do we need to find the value of our y? The reason is actually to be able to find the distance moved in the direction of the force when the body is released. And of course, that is what we are going to use to find our work done, because we said that the work done is the product of the force and the distance moved in the direction of the force. So if you do that, from this relation we have over here, we can have that x is then equal to 0.5 minus y, which is equal to 0.5 minus 0.25. And this gives us the value 0.25 as our x. Then if we substitute the value into the initial equation or the initial relation for the work done, we have that work done equal to the force times distance, so which is equal to F times X. And I said from the question F is equal to 0.1 times and X equals, this is in meters, and X is equals 0.25. And if you do this, we have that your value is 0.025 joule. And if you check the past question, we have options A to be 0.250 joule, option B is equal to 0.025 joule, option C equals 0.050 joule, and option D is equal to 0.500 joule. And the correct answer is 0.025 joule, and that is option B. Okay, I'm sure I have been able to discuss in detail what work done is. Like I said, this topic is divided into three: the work part, the energy part, and the power part. So we have come to the end of the work part. Of course, this is not the limit to the number of questions you can solve based on work. So in our next class, before we go into solving or discussing energy, we are going to solve one or two problems to better buttress our understanding of the concept of work. So see you in our next class. But in the meantime, if you have questions for me, you can always drop them and I will attend to them as soon as I see them. So bye for now.